So, good afternoon, everybody. Again, as I always say, this is definitely the place to be in Heidelberg. And today we're going to hear about a topic which is maybe not heard about enough, at least for people like me. We're grateful that Axel Brandenburg is here visiting, and I will ask Fritz Röpke to make the formal introduction. Thank you, Fritz.
All right. So also welcome from my side. It's my pleasure to introduce our speaker today, Axel Brandenburg. And looking at his CV, you can actually see that he had quite an affinity to northern locations, as far as I can tell. So he's from the very far north of Germany, started to study at the University of Hamburg, but then actually went further north for his PhD in Helsinki. And then there is kind of an oscillation between different places and always Scandinavian countries. So Helsinki, Copenhagen, in between people, other places in the north, like Newcastle, which is the north of England, I would say, Boulder, which is North America. Cambridge doesn't quite fit into the scheme. I would think this is south of England, but all the rest is very much in the north, and he's currently at Nordita. Axel is very well known for his work on MHD, simulations, hydrodynamics, magnetic fields, dynamos, and he's one of the, or the lead author of the Pencil code that is actually nowadays used by a very broad user base for astrophysical simulations. And he will tell us about these today, and I'm very much looking forward to his talk. Thanks.
Thank you very much. Thanks, Fritz, for your very kind introduction, and Richard for inviting me, and the audience for listening to me, and especially for the opportunity to answer your questions, hopefully during the beer hour, when I have the opportunity to speak to the students more specifically. I'm really happy to talk to you and answer what one might sometimes call stupid questions. These are often the best ones, and for me, the most interesting ones. Dynamos is a procedure which produces magnetic field in much of the universe. Think in particular, for example, of the magnetic field of the Earth. We thought for some period of time that the magnetic field of the Earth is something like a permanent magnet. But in the meantime, we have calculated how much is the conductivity in the Earth, and it wouldn't be strong enough to maintain the magnetic field. It would disappear after a period of time. So the magnetic field, even in the Earth, must be maintained all the time. But there's many other objects, the sun, other stars, and so forth, that all have magnetic fields. And so we need to explain them. But magnetic fields are not just at the scale of stars. They can also appear at the scale of galaxies. And there can be magnetic fields in all of the universe. Now, those mechanisms I would no longer call dynamos, but I will still talk a little bit about this because it is important to understand what exactly is a dynamo and what is not a dynamo. What you see here is a map in radio at a wavelength of something like 70 centimeters, I believe it was. And there you see some structures. And the reason why you see structures in radio is because of synchrotron emission. And synchrotron emission appears if energetic electrons, cosmic ray electrons, we call them, are spiraling around a magnetic field. And so it is immediately some evidence of a magnetic field in much of the galaxy and in much of the space even outside our own galaxy. The meeting is being recorded, it says again. Got it. That's why it didn't work. Right. When I was a child, I was playing with a little electronics box, and I was able to make a motor. And I therefore understand how a motor works. At least I was experimenting with this. I hope some of you at least had the pleasure of doing some electronics. A motor is what we have on the left, but the picture is the same on the left and the right. A motor works by having an electric current. That is the arrow so the magnetic field, this should be B, of course, and the current, I interchanged the two, I'm sorry for that. This should have been J, this should have been B, and J cross B gives the Lorentz force. And the Lorentz force exerts a material force on the wire. And so the wire therefore moves up. And if you calculate the J cross B here, it moves in the opposite direction. And so both wires are moved in such a way that you have a rotating motion. And that is what a motor is. But any motor can also be run in reverse. In that case, you would actually try to rotate this wire in the presence of an external magnetic field that is maintained here by permanent magnets. And an S refers to the north and south of the permanent magnet. And so once you have a magnetic field and you have a motion of the wire, you have a U cross B. And that one is called an electromotive force. The electromotive force multiplied by the conductivity of the wire gives you a current that would flow in the direction of U cross B, which is up here. So it's the opposite direction to here and around like this. So it's in the opposite direction. That's why a dynamo is exactly like a motor, but in reverse. So you just have to rotate, you have kinetic energy, and you can then convert kinetic energy into magnetic energy. In the old-fashioned dynamos, in the old-fashioned bicycles, we had really dynamos, and that's how that works. Nowadays, we have batteries. They are actually much better in many ways because we don't have these stupid wires always, which always break on my bicycle. But this is how a dynamo works. But there is a difference compared to this and astrophysical dynamos. The first important one is, of course, in astrophysics, we don't have wires, and everything is electrically conducting. And imagine you put this instrument into water, which is electrically conducting. You would just have a short circuit. And so the question really is it possible to have a dynamo working under the conditions where you would actually produce a short circuit? So it's not an obvious question, not at all obvious. The second thing is, what about the permanent magnets that you need here? And that is a question that has been answered already some time ago. And so the picture is here already. And that was a time of various engineers. Søren Hjort was one of them, Sam Worley, another one, Werner von Siemens, another one. And they all built very efficient dynamos that are then called generators because you produce electric power from mechanical power. You have a waterfall, for example, and the waterfall drives this generator and they have electricity. Or you have a windmill or something. And the important thing that really made these dynamos very efficient was to get rid of the permanent magnets that you need. And the way to do that is to simply tap some of the energy, some of the electric current that you have, and feed it back into the place of where previously was the permanent magnet. And so that's what we call a self-excited dynamo. And all astrophysical dynamos must be self-excited dynamos. In astrophysics or magnetospheric physics, another important field I was interested in when I was going to even north of Helsinki and so forth, going to the Arctic Circle, where you see the aurora. When the people, and I studied also the aurora, I was interested in that. In auroral physics, people also talk sometimes about dynamos. And in that case, they mean not the self-excited dynamos. They mean the dynamos that are driven by in the presence of the Earth's magnetic field. They also call that a dynamo. But in astrophysics, unlike magnetospheric physics, we talk about self-excited dynamos. And the question is really, can they work? Or do they not work? And this was a complicated question that was first proposed by Larmor from the Larmor radius in 1919. This was a pretty rough, speculative article. Nothing was meant to be terribly serious, but the ideas certainly made somewhat sense. But then there was Cowling, Tom Cowling from Leeds, and he proposed what is called an anti-dynamo theory, an anti-dynamo theorem. And it showed that a dynamo can actually not work, at least not under the somewhat simplifying conditions that he considered. And that was the assumption of axisymmetry. But this was not so obvious that that exactly was a problem. There could have been other problems. I mentioned, for example, that dynamos in this situation have to run under the presence of a short circuit. So it's really not very obvious that such a dynamo can really work under conditions where just everything is conducting. Nowadays, we have already laboratory experiments, and that comes in a few slides down, where we use liquid sodium. So liquid sodium is one of the best electrically conducting liquid metals. Mercury is another one, but not so well conducting. And so we better use liquid sodium, although that's more dangerous to work with. So dynamos work under these conditions, but that's only since the year 2000. And the very first time that we actually know that Cowling wasn't quite right in thinking that dynamos really don't work in general was several decades later. And there were fairly theoretical pieces of work by Herzenberg and Backus in 1958, which showed, yes, under some very specific assumptions, which don't exactly look very astrophysical though, you indeed can make a self-excited dynamos and not have a short circuit. In the meantime, there has been a somewhat different development, and that started already prior to the time of 1958, when we actually knew that dynamos can in principle work, and that was an attempt to understand the large-scale magnetic field that I will show in a moment of the sun. The sun shows, for example, an 11-year cycle, and it has a north-south asymmetry, anti-symmetry about the equator. And so this was an idea to try to understand. Gene Parker from Chicago, back then he was at Utah, University of Utah, was the first to envisage how in principle that could work. And he pointed out that a dynamo requires, or at least it can require, doesn't have to, but in order to produce a large-scale magnetic field most easily, he proposed that you need something like a swirling motion. And a swirling motion is what we have whenever something is rising, expanding under the presence of overall rotation. So if the sun is rotating this direction and you're expanding, you're conserving angular momentum, so you have to rotate the opposite direction. And so something which is then rising and rotating tilts immediately a magnetic field line, which is attracted with a fluid, into the perpendicular direction. It has a component then in the perpendicular direction. So that was his idea, but it was not mathematically too well founded. It was a correct idea, but not everybody believed in that. And so even his contemporaries didn't immediately understand the significance of this. Then there was another group of people in former Eastern Germany, Steenbeck, Krause, and Redler. And they proposed essentially the same, or they obtained essentially the same idea, but on a mathematically more founded basis. And so that became finally accepted. And then also Gene Parker immediately realized, oh, wow, I really had a good idea back then. So let's immediately expand on that. Parker was actually the first one who applied it then to the galaxies, but then also Weinstein and Rozmaichin in Moscow did similar developments. And in a completely parallel development, also from Moscow, there was a guy called Kazantsev, and he came up with a theory that had been overlooked for a very long time. And so that is what is called a small-scale dynamo. It does not explain the large-scale coherence of stellar and solar dynamos, but it is a mechanism that should work under much more generic conditions, and it's producing small-scale magnetic fields all the time, and you cannot even avoid it. So if you think of having Kolmogorov turbulence is what we call turbulence that produces a power law in the energy per spectral wave number. So there's a characteristic slope, and hydrodynamic energy is cascading from large length scales to progressively smaller length scales. That's the Kolmogorov phenomenology. And it is incomplete, according to this idea of small-scale dynamos, once the medium which you are considering, like a plasma, for example, is electrically conducting. And of course, plasmas are electrically conducting. And so that means that the ordinary simple Kolmogorov theory is incomplete in the sense that the magnetic field will immediately be excited. and it plays a role. It plays a role through the Lorentz force, it plays a role through Joule heating, for example, and so we cannot actually think of this as being unimportant. So Cowling's theorem, or anti-dynamo theorem, states in the modern form essentially that an axisymmetric magnetic field, not the flow, but magnetic field, cannot be generated by dynamo action under the assumption of axisymmetry of the velocity field, electric conductivity, magnetic permeability, everything has to be axisymmetric, and the shape of the conductor. That sounded very straightforward, and there's actually one little snack with this, and it's also not quite the right one. That was a recent realization by a group just a few years ago, and I mentioned that. But the struggle for acceptance was really quite remarkable. Larmor, immediately in the year after Cowling's anti-dynamo theorem, wrote in his rebuttal the theory proposed by Sir Joseph Larmor. He was quoting Cowling's paper in quotes, the theory proposed by Sir Joseph Larmor, that the magnetic field of a sunspot is maintained by its currents it induces in moving matter, is examined and shown to be faulty. But then he continues toward the end of his paper and says, so that if this theory is to be demolished, there's no explanation of the sun's magnetic field even remotely in sight. So that was a correct analysis, but it wasn't well understood. Remember, it was only in 1958 that we actually mathematically had the first existence proof of a dynamo. So from that time only onward, we know that a dynamo does not actually still work under conditions that are almost short circuit. So Parker's paper was of 1955, but here's a paper of 56, 1 year later. And Parker's paper was submitted, by the way, 54 even. And Parker and Chandrasekhar had been colleagues, at least slightly afterwards, when both of them were in Chicago, and Parker wrote the paper on the solar wind. He had a simple understanding of the first understanding that the atmosphere of the Earth, of the sun, doesn't have to be in hydrostatic equilibrium. It can be in a steady equilibrium where you still have a flow all the time. Rather remarkable. I mean, if you wouldn't think that the wind here, for example, would all of a sudden steadily go upward. You need a source, of course. Now, the sun has in principle a source. For the corona, it happens. And it actually has a steady solution with a finite velocity. And that was due to Parker. And that paper was, of course, also rejected by the referees in the beginning. And then Chandrasekhar was the editor. And he was wondering, what should I do with this paper here? And then he asked Parker himself, because he trusted Parker so much already. And Parker said, yeah, but the referees are not saying anything is wrong. They just don't believe it. That's all. And so then that was good enough for Chandrasekhar as the editor-in-chief to accept that paper, and it really played an important role and was a correct understanding at the time and even nowadays. But what Chandrasekhar wrote even then was that velocities of reasonable patterns and magnitudes can alter the decay. And remember, the decay of the Earth's magnetic field was too short to understand the existence of magnetism at the present time, after the age, given what the age of the Earth is. So the decay will be such that will slow down the decay compared to the case in the absence of motions by quite large factors. That is also a correct understanding. So you can have situations where velocity fields usually they would speed up the decay by mixing things, but they can, under certain conditions, also slow down the decay. That is indeed correct. But it shows you that even Chandrasekhar, even though he already knew that in principle, or could have known that Parker, his colleague, has the right understanding, he thought, oh, maybe that's still not the right understanding, and maybe there's some other reason for explaining, for example, the Earth's magnetic field. So he found these large factors by which the decay can be slowed down. So Parker, remember 54, he had actually not just a dynamo paper, hydromagnetic dynamo models, but he also had a paper in the same year and not only the same year, but actually the same day submitted, October 18th, in both cases. And by the way, only one of them shows revised. So this one was probably accepted straight away, and maybe even without refereeing. This was a time when refereeing became just popular and was not always required. So the other paper, not to be confused then with the Dynamo paper, was one of explaining why sunspots usually come in pairs. So we have an underlying magnetic flux tube that then can become buoyant because the tube itself has magnetic pressure, which means under pressure equilibrium that the gas pressure has to be lower, and therefore the density has to be lower, and therefore it becomes buoyant and rises and expands. But this is part of the idea also that is required in the dynamo, because you have in this type of large-scale dynamo where you have a rising string or set of tubes that rise and then get tilted and produce a component that is somewhat tilted relative to the toroidal direction in which most of the magnetic field points here. I say toroidal because the presence of rotation, the sun is not rotating rigidly. We know the surface of the sun is gas, it's not rigid. And we also know that at the surface of the sun, there are sunspots. If you look at sunspots closer to the equator, they have a faster rotation period than those higher to the poles. Quite remarkable. And this result means that the surface of the sun is not rigid and there's differential rotation. And so this differential rotation would make any magnetic field that is not aligned with the toroidal direction would try to always make it toroidal. And so much of the magnetic field is therefore toroidal. And so the question is really, how can you then produce a magnetic field in the perpendicular direction so that you can continue shearing it out and thereby amplifying it even further? That was the reasoning of the model of Parker. But this is only one of the mechanisms, it's perhaps the most important one, but it's not every dynamo has to be that way. So these were the equations, and that's Gene Parker himself. And for the large set of discoveries that he made, I mentioned already the solar wind, I mentioned sunspots, I mentioned the dynamo. There have been many more, also having to do with cosmic ray understanding, acceleration. He got what is called the Crafoord Prize. It's given by the Swedish Academy of Sciences in 2020, but this was a time of Corona, and so he didn't actually travel, and there was no prize ceremony in 2020, and not even 21 there was a prize ceremony. His son, his younger son, Eric Parker, came therefore to Sweden to pick up the medal and gave it to him. And there was a photo. I saw the photo. I haven't actually taken a screenshot of that. But unfortunately, he died just in March 2022. And the ceremony was finally in April 2022, just 1 month later. And so he saw the medal. There was a picture where he had proudly the medal in his hand, but he was not having the opportunity to be awarded that medal in person, unfortunately. His basic idea works essentially like as follows. You start, and this is a sketch of the sun, different perspectives. Here you see it from the side. Here you also see it from the side. Here you see the northern hemisphere from the face on. Consider a magnetic field that is a poloidal loop. Poloidal meaning it's in the plane from pole to equator, for example. A loop that is closed like this here, and then under the presence of differential rotation in such a way that it's faster in the inside than on the outside. Then a vector like this, which points outward, is being tilted in such a way that the inner parts are rotating more rapidly. And that means the arrow of the magnetic field gets a component that is pointing in the negative phi direction, westward. That's the negative phi direction mathematically. Down here, the arrow points inward, but then the tip is accelerated faster than the surface is, and so it moves eastward, mathematically positive direction. So you have two different toroidal magnetic fields from this initial poloidal magnetic field. The question is now, can we maintain such a poloidal magnetic field? And the answer is yes, provided you have this, what I explained, a rising of a magnetic field but in the presence of expansion. Why does it expand? Because the density is less in the upper parts than in the lower parts. It's like a hot air balloon. It rises and expands. And then it, under the presence of overall rotation, it receives a tilt so that you have a new poloidal component. And this new poloidal component has an orientation in this direction. Up here would have the opposite direction. And what you now see is instead of having one poloidal loop, you have two. And this one with the orientation pointing towards the equator has moved equatorward. And so not only have you explained that you can regenerate loops, you have even explained that they would also migrate toward lower latitudes. And that's exactly what we see at the surface of the sun. Here's a magnetogram versus latitude, or the cosine of latitude, going from +1 to -1. And here's time. Here's the year 1980. Here's the year 2000. You see patterns of strong magnetic fields of negative polarity down here, positive polarity in the opposite hemisphere. And with time, this pattern moves toward lower latitudes. And that's exactly what this picture shows here. So this was the overall understanding of how Parker understood this thing. Here you see the evidence from magnetograms. How do you observe magnetic fields in the sun? You do it with circular polarization. Circular polarization, one of the three lines of Zeeman splitting, is being circularly polarized, and in such a way you can measure the line of sight magnetic field and direction. And so black means inward, white means outward. And so you have two different polarities close together. And that's exactly this picture of a bipolar region, which I explained to you earlier, which Parker believed to be the result of magnetic buoyancy, which leads to this rise and tilt. So this is the overall idea. You have poloidal magnetic field. You have what is then called the omega effect, differential rotation, omega for rotation. It produces then this toroidal magnetic field. And then you have what Parker called, actually not the alpha effect, but it was alpha effect, called in the theory by Steenbeck, Krause, and Redler in '66. I will probably not go through all, the other examples of dynamos, unless there is really enough time later on. But there are indeed other mechanisms that can also produce a large-scale magnetic field. But this is most likely the most important one for much of astrophysical dynamos. So alpha effect came from this paper by Steenbeck, Krause, and Redler, and alpha is simply one of the first letters in the alphabet, of the Greek alphabet. Beta is the next one. And so what they calculate is U cross B. Now, or V cross B, V for velocity, B for magnetic field, prime for fluctuations, and overbar for mean fields. And so what you're now doing is you're doing a theory not for the actual magnetic field, but for the averaged magnetic field. So you have to have the induction equation. You average the entire induction equation, and the induction equation has already this term U cross B that I explained in connection with the dynamos. But you have to average that. And that has two contributions, one from the averages, the mean flow that produces the omega effect, and the mean magnetic field. But it also has fluctuations, and they're called primes. So fluctuation is the departure between the actual velocity and the averaged. So you subtract the average to get the fluctuation. And if they correlate in such a way that the cross product is finite, then you could have various components that point in different directions. One could be potentially in the direction of B, and the other one is in the rotation, in the direction of the rotation or the curl of B, which is the electric current. Now, the component in the electric current is something that we have already in the induction equation. It leads to the ohmic diffusion, ohmic dissipation. And so by having such an extra term, you're basically enhancing a term that is already present in the original induction equation. And so it's called turbulent magnetic diffusion, as opposed to microphysical magnetic diffusion. So this is a term that is a result of analyzing, calculating, doing a rigorous calculation of this correlation. And it leads to the fact that there can indeed be a net contribution that actually enhances magnetic diffusion, potentially by quite a lot of orders of magnitude. A similar concept is also known for the viscosity. There's something that is called the turbulent viscosity. And the first models of accretion disks go back to Shakura and Tsarnaev, a paper with more than 5,000 citations, maybe 6,000. And it uses, of course, the fact that the viscosity in an accretion disk is not molecular. It's a much, much stronger one. And so this is a similar effect here. But then there's another effect that actually points in the direction of the magnetic field. And this is structurally different. Let me briefly explain this. The current is a quantity that is the curl of the magnetic field. And so we have two different types of vectors, ordinary vectors that point in the same direction if you look at this in a mirror. But imagine, for example, you have rotation. Rotation, you should actually not think of a vector, you should think of something which is called an axial vector. So you think of just the motion of your hand. And if you now look in a mirror, then your motion of your hand is being reverted. And so all of a sudden, this vector, the tip of the vector points in the opposite direction just because you look into this in a mirror. Of course, it wouldn't do it if you think of such a vector as being a vector with an ordinary tip. You should think of this as being an axial vector, which has this motion with your hand. And so there are these two different types of vectors. And so one of them is this one, the other one is this one. And so this is a quantity that also is an ordinary polar vector, as we call it. And so this is therefore an ordinary scalar. However, this one, if you connect an axial vector like B field with a polar vector, then this scalar is not actually an ordinary scalar. It is what is called a pseudoscalar, which changes its sign if you look in a mirror. Anyway, so this must therefore have a somewhat non-trivial reason. The only reason that you can have an alpha if there's something in the turbulence that is violating mirror symmetry. And of course, the swirling motions with rise and stuff like this, they are all doing this kind of stuff. So for here, for example, they calculated that it is the product of velocity fluctuation multiplied with the curl of the velocity. That's called the kinetic helicity. So this paper by Parker, as I said already, was not actually noticed so much, not even by Chandrasekhar, until actually this paper came out and achieved. And so with this paper alone, Parker's paper all of a sudden began to get a significant amount of citations, and the number of citations has been increasing ever since. So Steenbeck, and this is from the book by Günter Rüdiger, the memoirs of Günter Rüdiger, one of the people from that originally group in Jena, Eastern Germany. And, you know, we have usually these DFG meetings. Of course, they are always all of Germany, but during the Eastern times, there were two different types of meetings in the East and the West. And there was the last one, which was in the year 65 in Eisenach in former GDR, the last all-German astronomers conference, where Steenbeck, up here, the first author of that paper, the group leader, was proud to present his paper in the presence of famous other astronomers, including Kippenhahn, Weigert, Metzger, and so forth. And after Steenbeck's lecture, where he thought he was able to announce the understanding of the magnet puzzle, as he thought, it actually resulted in somewhat of a disaster in the sense that nobody asked any questions. There was silence. And there was no applause. Everybody was somehow shocked or surprised. And Steenbeck was massively upset and immediately drove back to Jena, leaving his colleagues behind. So this, you must have imagined, is really a tough time where you think you have understood something and all of a sudden there's no response. In the meantime, remember I mentioned one paper, namely the one by Kazantsev, which is the one which Kazantsev in 65 was overlooked for a long time. Yes, the reason was it produced something like what is called a small scale magnetic field. And here's a very simple model of that. You take an original magnetic flux loop, you stretch it, you twist it. By stretching it, you maintain the flux, but then you twist it into an H-shaped figure and fold it back in exactly such a way that you have a constructive addition of the fluxes. And so all of a sudden you have multiplied the flux by 2, after having merged this. And so you need a little bit of diffusion in order to accomplish this step. And diffusion, it turns out, is something that is actually indeed not trivial. You do need microphysical magnetic diffusion in order that any dynamo can work. So this was completely independently obtained from first numerical simulations of turbulence. And remember, I mentioned to you, when you have turbulence, you will automatically have, even in the absence of velocity and nothing, you will always have some small-scale magnetic field, or even a strong small-scale magnetic field. And the first calculations were in the year 1981 at moderate resolutions of 32 cubed and 64 cubed. And then there was even a paper of 92 by Russell Koolsrud and his student. They basically showed, and this was in full agreement with the condenser theory, without him knowing about this paper, completely he generated the same theory. It's a theory for the magnetic energy spectrum. So it's a theory for the fluctuations themselves, and they produce magnetic fields that can lead to exponential growth at the rate of gamma against magnetic diffusion. So this was what is called the small-scale magnetic field. Here are the laboratory dynamos. Here, this is the model in Karlsruhe, where you pump liquid sodium along a channel, but you explicitly make sure that you have helical motions by having diverters in these tubes, which makes the flow swirling. So it's a bit artificial, but at least it led to an explicit dynamo action. The magnetic field rose away from 0 to a positive value. The reason why it's positive is because it's not exactly 0. There's the Earth's magnetic field. And so therefore, depending on how the system is being arranged, here are these tubes, and liquid sodium pumped from one to the next tube and out again. I saw this with my own eyes, and I heard it, of course. You have the engines running up and up. And you hope, of course, that nothing explodes. And you look at the magnetometer, and the magnetometer increases. And so you really saw that and I saw it with my own eyes. Very impressive. There's a lot of other different types of dynamos. One of them is the experiment in Riga. Here's another one in Cadarache. And this is a future experiment which works in the presence of what is called precession. The presence of two different axes, an axis rotating around this huge table here, and another one at a certain inclined angle. And this comes from potentially the Earth's motion. So here you see the animation of a numerical simulation, and on the right you see what is shown called a power spectrum. You see that the kinetic energy spectrum has most of the power at this peak here, and magnetic energy gradually develops power at lower and lower wave numbers, which means larger and larger length scales, until the end you have a magnetic field that extends all the way over the scale of this periodic box. Now, a star is not periodic. A star is in a sphere or in some other shape. And so, of course, these results will depend on how exactly these things look like. I will skip a few things, but will say that there is one important or interesting, remarkable experiment which showed that a dynamo loop can even be closed by modifying, making the conductivity anisotropic. And so that's another thing which violates the original Cowling theorem. So it's possible to do it, of course, in a copper bar. So these are not liquid metals, but these are solid metals, but they are rotating, and they are maintained and contained in another conducting exterior. And so by having these lamelles, conductivity is preferentially getting an azimuthal component. And that makes this conductivity non-axisymmetric, and you are able to produce a radial magnetic field from a toroidal magnetic field by having, this one corresponds after taking the curl to a radial current, but you have a conductivity that has a component in the theta and phi directions. So magnetic fields also work on galactic scales. They can, and that was realized by Parker in those years. The idea, however, was, or it turned out that in order to make a magnetic field on galactic scales, it's not only harder to do so large length scales, it also takes a lot more time. And so because of this, it was and it's still not 100% clear whether we are able to make enough magnetic field within the amount of time that we have, namely 10 gigayears at most. And not only that, most of the observations of magnetic fields that have an age of just 1 gigayear, and they already have potentially significant large-scale magnetic fields. So that's not obvious to explain. And so, so therefore, one idea was that the magnetic field could actually be something like a primordial magnetic field with a large-scale component from wherever it comes from, not explained, of course. It's a competing theory. But then whenever you have a galaxy, it would wind up a magnetic field in such a way that it winds up. So the magnetic field originally goes from up here to there. You would wind it up. It would go back. So you have a component of the magnetic field that here goes out, here goes in, and then here goes out again, and here goes in again. So if you do a circle, if you observe the magnetic field along a circle, and imagine the galaxy is slightly inclined so that you can actually see the part of the toroidal component, what you would see is that the magnetic field would reverse its direction twice as you go around in a full circle, as opposed to the situation where you have an axisymmetric magnetic field. And in that case, the magnetic field, the line of sight projection of the magnetic field would only revert a single time. Here you see the magnetic field would point away from you. If you see it slightly inclined, this is maybe a better picture here, and here it would come toward you. And so that explains these two different signs of line of sight components. And you can measure them by making use of what is called the Faraday effect. Faraday effect means that you have synchrotron emission, but this emission is being, and it would have a radial component of the magnetic field, but this, but any of the vectors that are being produced are being rotated, or the polarization vectors, at least, that is caused by the perpendicular component of the magnetic field, is rotated along the line of sight. By the more you have the stronger the line of sight magnetic field component is, and the stronger the electron density is. So you don't quite know what is due to the magnetic field and what is due to the electron density. But you basically can measure such thing, and that has been done. There's another thing, and that comes in the X transparency, and that was first pointed out in this paper by Parker, submitted already in 1970. I remember Parker immediately came up with lots of different ideas. There was a huge range of papers, including a book shortly afterwards, where he understood his idea of 55 really made sense, and other people began to understand that. And an important other piece was there was actually a translation into English by Stix from Freiburg and Paul Roberts from Newcastle at the time into English. And so much of this work became then understood to much of the West. And so one of the important results already of Parker's paper was that the magnetic field, the large-scale magnetic field in the galaxy, would produce mostly a toroidal magnetic field that is even. So even means that the toroidal component, here indicated by a tip toward us, has the same sign in the northern hemisphere and the southern hemisphere, as opposed to one where it has opposite signs. You would have an opposite sign if the magnetic field has essentially like a dipolar structure. I call it dipolar because it's not a pure dipole. There's higher multipoles, but all of them are odd. And that's what we mean by dipolar, as opposed to quadrupolar, which means that all the modes are even. And so Parker was already the first who found that the magnetic field would have mostly such an even mode at a time when it was not even well observed. Nowadays, we observe many galaxies, and we observe that many of the magnetic fields are indeed even about the midplane. And not only that, most of the magnetic fields are actually not non-axisymmetric, but they're actually axisymmetric. And so most likely they are not produced by winding up a primordial magnetic field, but they are produced by dynamo action. That would be the only strong alternative in this case. Some numerical models of this. You remember the sine and cosine features here. That is also obtained roughly from some of our early numerical simulations. Here is an axisymmetric magnetic field. Here is the non-axisymmetric magnetic field. Looks not so nice, of course, but So finally, in the last few minutes, let me say a few words about primordial magnetic fields. When I was young, 30 years ago, and was starting in this business, I always thought primordial magnetic field is boring because you basically remove the origin of magnetic fields to something which you cannot well understand. And then you're not using dynamo theory, and so I found this all pretty crazy. In the meantime, I've realized that primordial magnetic fields, okay, it's not a competitor against magnetic field generation in galaxies, but it's a very nice, interesting research topic in its own right. And there are ways of potentially observing it. So we see, we have in cosmology a lot of big space, but there's also spaces in between galaxy clusters. Here are not only galaxies, but clusters of galaxies, many galaxies together. And then there are regions without just anything. And they are called the voids. And of course, explaining magnetic fields in galaxies, we just learned, is potentially possible with a dynamo. We can already do it in stars. Galaxies, as I said, maybe the timescales are not quite okay. But how can you explain such a magnetic field if it's present in such a void, if it is really present in such a void? We don't know for sure yet, but there are strong reasons to believe that even here is a magnetic field. And that's important. If that is really true, we don't think that astrophysical mechanisms can be responsible for that, and there must really be something primordial. Primordial means before astrophysics began to play a role. So one of the ways of measuring this is by looking at the secondary emission from blazars. Blazars are very strong accretion disks. They have jets, they produce extremely energetic photons, TeV, tera electron volt photons. They would interact with the cosmic background light. They would pair create electrons, positrons. They would divert in opposite directions and would not potentially recombine. And so you wouldn't have the secondary radiation, which would be at GeV levels. And so based on that idea, there must be, if you don't observe, and one does not observe the secondary GeV photons, there must be at least some kind of magnetic fields, which is plotted here, versus the corresponding length scale. And very weak magnetic fields must be excluded, because they would, of course, not be able to lead to the secondary, they would not disrupt the secondary emission. So we know that we have magnetic fields on the order of 10 to the minus 16 Gauss approximately on a megaparsec length scale. So primordial means very early in the universe. This means times of when the universe was maybe 10 to the minus 10 seconds old, or maybe even earlier during the period of inflation. And both of these times can potentially lead to a magnetic field. Let me just say a few words about this. And let me also skip this one here. So one mechanism is called the chiral magnetic effect. And that would be a situation that could potentially work at the time of the electroweak phase transition. So there's physics which can produce particles. And these particles, when you have a neutron, for example, would decay into a proton and an electron. And an electron can have a spin, or has a spin, and it can either be aligned with the direction of its momentum or anti-aligned. And spin is a polar, is an axial vector, similar to what I explained a moment ago in connection with turbulence. Here it's not turbulence, nothing has to do with turbulence, it's just microphysical theory. Can either be aligned or anti-aligned. Here is aligned, here is anti-aligned. If it's anti-aligned, that's the situation with if the universe is dominated by matter. So very similar to the dynamo theory I explained, there is a possibility of producing a term in the induction equation, which now has to do with the magnetic field. And we learned already that such a process can lead to amplification of magnetic fields. And that's indeed true. There's no surprise, actually, in this theory, because we understood already that dynamos work with this Parker theory. This is essentially the same thing. So it shouldn't be a surprise, and indeed it does work. The reason why we have a current is because the magnetic field aligns the spin of the electrons, and because the momentum has a certain direction with the spin, it means there will be a net current. Electrons are electrically charged, so charged particles move in one particular direction now. That leads to a current. So the way how such a thing looks like is you produce magnetic fields predominantly at a particular wave number, which is shown here. And you see that the magnetic energy rises at this wave number, but then it propagates to larger and larger length scales. And that's very characteristic of situations where you have helical magnetic fields. This helical means that the magnetic field has current in the same direction, and the cross product, dot product of these two vectors is therefore a pseudoscalar. We know from this that there's a certain strength of the magnetic field at the present time. So we have generation which could produce something like on the order of originally 10 to the -6 Gauss, a micro-Gauss. It would then decay and also increase its length scale. That's what is called an inverse cascade. And so these are different trajectories that we are now beginning to understand. And it depends on the presence of certain conservation laws, whether, for example, the magnetic helicity is indeed present initially or not. So there's three different observables that we mentioned. One of them is looking at the structure formation. The other one, and that's very remarkable, is looking at potentially primordial gravitational waves. So that requires instruments either in space, or we have also what is called pulsar timing arrays that can measure on much, much larger frequencies the polarization. So gravitational waves is something remarkable. They can show a plane of polarization which rotates. So gravitational waves has to do with these two different modes that are expanding, and that leads to a polarization plane that can rotate, and it does rotate all the time in the temporal fashion, but also in space, because now you must imagine that you have many of these, and so they're all at a different rotation, but they all rotate in the same direction. And so gravitational waves has to do with calculating a certain tensor, therefore they're called tensor modes, and if they are being produced by a magnetic field, especially such a magnetic field, and such a magnetic field, if you take the curl of this, gives itself the same thing. So taking the curl of such a thing gives you the same vector, and therefore its curl is aligned with its original. That means it's helical. If such a thing is helical, you also produce off-diagonal components in this tensor, and that's why the circular polarization plane has a certain sense of rotation. And that is indicated by this red letter here, the sigma that you see down here. Okay, so let me say these are very interesting prospects of potentially observing the existence of primordial magnetic fields at very, very early times. There's even inflationary magnetogenesis. It's a different mechanism. What is remarkable there, it also works with an equation that is linear. And so you can have, again, instabilities. And they come from the fact that inflation leads to tremendous stretching of space-time. So let me now come to the conclusion. It has been exciting to expose you to this wealth of information about magnetic fields, not only in stars or the Earth, but also in galaxies and even the universe as a whole. So dynamos work in principle always if the conductivities are large enough. That means the Reynolds and fluid Reynolds and magnetic Reynolds numbers are large. There's different types of dynamos. I mentioned the small scale dynamo, for example. So every turbulence itself will always produce magnetic fields. A non-magnetic state hardly exists, except perhaps in the Earth's atmosphere where there's not much conductivity unless you have a lightning for that short moment of time. But magnetic fields can also be produced in the early universe, and it would be exciting to observe gravitational waves, circular polarization in the future. So there's a lot of stuff to come in the future when we can hopefully wait for the LISA space interferometer. Thank you very much for your attention.
Thank you Axel, for this very intuitive and for your wisdom explaining the historical developments too. We have time for maybe 2 or 3 questions. So please raise your hand if you would like to ask one. So that's one.
Okay, so very interesting presentation. Also going along the history, it's very nice to see. Yes.
Yes.
So I have a question about the cascading, because you started with the Kolmogorov spectrum. Yeah?
Yes.
Energy is cascading to smaller scales.
Yes.
In all the dynamos, it seems the other way around. Is there a simple argument why the energy is transported
there's
to
an
larger
argument
scales?
for that, and the argument has to do with the conservation law of magnetic helicity. So remember, magnetic helicity has units of b squared and length scale. And if this quantity must be constant, but the magnetic energy is decreasing, the length scale must increase, because the product of b squared times lambda, the length scale, is constant. Right? Magnetic helicity has this, if it's fully helical, it can be approximated by Schwarz inequality by b squared times lambda, the length scale. This must then be conserved. And so if b squared decreases, lambda must increase. So you actually cascade inversely. And there was, in fact, one picture I skipped over, and there you see that very explicitly. You saw it already from this one picture earlier here, you saw it also. But here, for example, you see spectra. In hydrodynamic turbulence, you don't have that. You just have that the energy decreases. The length scales do increase a little bit, but the energy does not increase at the smallest wave number. But in the MHD case, with helicity, you have an increase of the energy at the smallest wave number, but also a decrease of the wave number, meaning increase of the length scales. Even in the absence of helicity, you have inverse cascading, and that's another completely new result. Which has to do with another conservation law. Was that answering your question? Yes. Thank you.
Okay, thank you. Another question from the floor. Ralph has a question.
So, very nice, very nice. About the generation.
Yes.
Values compared to the kinetic energy with France.
So you ask how strong the saturated magnetic field energy can be?
Yes.
Yes.
And what are typical values, and on what does it depend?
So it is often in the proximity of what we call equipartition strengths. And so that means that the magnetic energy density will be comparable to the kinetic energy density. And in galaxies, we know that as an empirical fact. You measure the velocities, they are 10 kilometers per second. You have a certain density of 1 particle per cubic centimeter. You know how heavy a proton is. And so now you calculate magnetic energy in Gaussian units. B squared divided by 2 pi is the magnetic energy you calculated, and it corresponds to approximately 3 microgauss for the galaxy under conditions of interstellar turbulence. So equipartition is the typical answer, but it doesn't have to be exactly, and it can even be more magnetic energy. Just for the same reason that if you have a waterfall, then locally, or if a river, if the speed of the river is high enough, the water levels can rise to tremendous levels, as we have seen some years ago in the R level, in the R river. So equipartition is the rough answer. But there's different sources of energy. There's also the stretching, of course, from the toroidal motion. But most important is the turbulent magnetic energy. And so typically equipartition between turbulent energy, magnetic energy, even cosmic ray energies, and thermal energies in the galaxy. All sort of similar ballpark figures. Yes, there's one more question and 2 more questions.
Brian?
And of course, I will be happy to talk to the rest of you over beer in a moment.
Thanks, Axel. You mentioned quite a few times about these liquid metal dynamos, but of course, liquid metal is not a plasma. So what kind of numbers are you expecting in these, and how would these compare to astrophysical? So Reynolds numbers in the...
Right. So one problem with liquid sodium is otherwise it's perfect. There's no big difference between a plasma in some sense. One mistake that one can commonly do is you think of a plasma being full of charged particles. That's true, but you have positively and negatively charged particles. And so locally, you just have as many positive and negative charge carriers. So it's neutral. There's no net charge, and anywhere in the plasma, by and large. So the same with liquid sodium, or the same with a wire. There's no net charge. You have just positive and negative charge carriers moving all the time in opposite directions. One problem with liquid sodium is that the viscosity is low, but the magnetic conductivity is poor. And so the ratio between magnetic diffusivity and the magnetic viscosity, the viscosity and the magnetic diffusivity, that ratio is actually small, 10 to the minus 5. That's similar to the sun, but it means that if you have huge fluid Reynolds numbers, the magnetic Reynolds number cannot be huge anymore. You have a fluid Reynolds number of 10 to the 7. That means the magnetic Reynolds number is just 100 approximately, 5 orders of magnitude less, which is just marginally big enough. So it's much harder to do a dynamo in liquid sodium. It's just about possible, and let's hope. And you need large enough length scales. So this thing that is built in Dresden now, this precession, has a size of, I think 3 meters. You have seen the picture of a man. It's small compared to the thing. Everything is super dangerous, of course, but plasma experiments is also something, but you need to drive the plasma, you need to maintain it. It must be maintained. That means it must be hot for long enough. So in ITER is the fusion reactor in future in Cadarache. Of course, we hope that it will run for 50 minutes and the plasma will not break out. So yes, they are similar actually, but we cannot reach really very large Reynolds numbers, magnetic Reynolds numbers. So the existence of a dynamo, we can just about begin to prove, but we cannot explore really astrophysically interesting things. So we need the computer to simulate that.
Okay, I think we have time just for one last question.
Can you probe the primordial magnetic field? I didn't quite.
The primordial magnetic field, yes. So there were these 3 different methods. They're somewhat indirect. One of them is, of course, having to do with the TeV emission from quasars. Remember? I explained that briefly. They interact with the cosmic background radiation of very low energies, but they still produce GeV photons. They should produce GeV photons. We know that from numerical calculations, also from measurements, but we don't see enough. And so then there must be a reason for that. One of them is plasma instabilities, and we heard from experts saying that indeed they would not be efficient enough. And so magnetic fields is the only other reason. So we must have a magnetic field that then disrupts this cascade. And then there's a third method. I didn't have time to go into that, but it essentially is also related to that, and it would be to actually see some signal from that, and you would look for a swirl, a pseudoscalar in the sky from the arrival directions of photons. It's quite remarkable, but you can produce a pseudoscalar, it doesn't matter. From the arrival direction, you take a cross product of 2 vectors, and you need a third vector with a dot product that gives you a pseudoscalar. Not immediately related, but once you have a pseudoscalar in the system, it might explain the presence of other pseudoscalars in the system, and this is one of the examples. So there's these 3 methods.
Yeah, but how does LISA? You mentioned LISA specifically.
The what?
LISA, the LISA experiment.
LISA,
yeah.
Yes. So LISA means we are looking for gravitational waves. Right. And now we need to, of course, hopefully measure circular polarization. How do you measure that? So we need not just LISA, we need the Japanese, the Chinese equivalent to LISA, which has another name, I forget now. Does anybody remember that? And so both of these should be, of course, aligned or arranged in such a way that you can potentially measure the different orientations of circular polarizations in the sky at different positions. So you need separations by a fraction of an AU, and you would measure circular polarization axes that are different in the different positions. And that means you have circular polarization, just like the optical circular polarization. You can then measure it, and the existence of a net circular polarization, which is the same all the time at different positions in the universe, right, would be a very strong signal of a underlying helical magnetic field. Okay. And we have calculated that, and that's all part of the pencil code, and you can do these calculations and simple models also.
Thank you.
Thank you. So let's talk more about this over beer.
Yes, I think there's a lot to discuss here. Well, before we thank Axel for this very, very interesting colloquium, I'd like to point to next week, where we'll be hearing about the death of How Stars End Their Lives from Philip Podsiadkowski, who is visiting professor here at HITS. So you can discuss all your topics on magnetism over a beer, as Axel suggests.
And even astrobiology, I have done some work on, for example, the chirality of the handedness of biomolecules, for example. Sugar is also different from its mirror image. I have been working on how this comes about, and we think it must be the origin of life, the moment when it was decided that our life has one specific handedness. If you have an independent genesis of life on Mars, for example, not impossible, it might have the same or might have another handedness. So these are all fun topics to research and hopefully also to connect with experiments.
Yes, I think it's very exciting to see the connection between theory and experiments, particularly in this colloquium today.
Exactly.
Thank you so much, Axel, for a wonderful, informative colloquium. It'll remain in our minds for some time, I think. Thank you.
Please. Thank you.